The idea came mostly from my 8-year-old version of myself. My first trip to the beach, I was collecting seashells and I was quite fascinated with how this material was actually formed.
Maybe you too had this thought as a child, but for Ginger Krieg Dozier, the idea inspired her to change the very ground beneath our feet.
Something.
Ginger is the co-founder of BioMason, a young biotech startup in Raleigh, North Carolina that uses, wait for it, bacteria to grow cement bricks. Regular cement is in sidewalks, roads, bridges, and buildings. It's everywhere, but that creates a hefty environmental price, 2 billion tons of carbon dioxide each year. In rapidly developing countries, cement is critical for construction, but to halt global warming, net human carbon emissions must reach zero. Zilch. By growing cement bricks, BioMason eliminates the carbon emissions. Let's find out how. Cement's carbon problem starts with limestone. To make cement, limestone and other minerals get roasted at 2,800 degrees Fahrenheit. Whew, that's hot. Fossil fuels burn to power these ovens, plus a chemical reaction that turns limestone into cement, create carbon dioxide, a lot of it. Cement making accounts for 5% of global carbon emissions, which seems small relative to car exhaust or power plant fumes, but it's still more than all the airplanes and ships in the world, combined. A decade ago, these realities hit Ginger like a load of bricks, and at the time, she was a young architect interested in new age building materials.
I came back to that seashell and coral and tried to understand where maybe we can grow materials the same way that seashells and coral is actually grown.
Seashells are hard because of calcium carbonate, the same tough stuff in limestone. Organisms in nature love making calcium carbonate. Oyster pearls, coral reefs, and your teeth and bones are reinforced with it. And some bacteria make it too.
The calcium carbonate literally forms around the cell of the microorganism, basically encapsulating them in between the grains of sand. So you're literally stitching them together.
We asked Robert Jackson, a Stanford environmental scientist and chairman of the pollution-fighting Global Carbon Project, what he thought of the biocement concept.
In principle, we can harness the power and the ingenuity of microbes to make some of these materials. You still have to have a source of energy though, and there are a lot of other details to work out.
This is why BioMason is noteworthy. Their bacteria don't require extra heat or high energy to make the biocement. The chemical reaction needed to make calcium carbonate is powered by the microbes' metabolisms. For bacteria in nature, this process would be slow. The right feeding conditions may occur once every few years. But in the early days, Ginger and her husband, co-founder Michael Dozier, discovered a way to speed things up.
This is a liquid culture of our bacteria, so it's a liquid version of what happens in the bricks.
After 111 failed experiments, the pair found a microbe in the soil that did the trick. It's a strain of Bacillus bacteria that doesn't cause disease and isn't genetically modified. Instead, they found the microbe's optimal conditions for making biocement. Just add calcium and voila, instantly made calcium carbonate crystals. With that key process solved, they could make biocement using no more than the energy required to keep the lights on. These days, their assembly line fills a warehouse. The process starts with foundation material and a machine that can make up to 10,000 bricks at a time.
This is an inert material, it could be sand or a crushed stone.
Here, a pitcher of bacteria is poured into red sand, and after mixing for 5 minutes, everything gets dumped into the hopper. This machine funnels the wet sand into individual brick molds, which then get covered with a pressurized plate. Okay, hold on, because this part is pretty loud.
You imagine you pour sand into a cup and it just sits kind of fluffy, but if you put a plate on top and vibrate it, those particles shift around until they nestle and find their home.
The final bricks get pulled out like bread rolls on a tray, and then are wheeled into a shipping container where they harden over 3 to 4 days.
One of the advantages that we have is that the cement itself is an off-white.
This blankness creates a canvas for playful designs. They can make old and burnt-looking bricks without using fire. But does biocement hold up like regular cement? To find out, a handful of bricks from every BioMason batch gets tested for quality control. The bricks face things like extreme cold, or water erosion, or immense pressure to see when the bricks collapse. This one split after more than 23,000 pounds of force, which far surpasses what a brick would face in a 3-story building. But meeting industry standards in a lab is one thing.
Field testing has included 2 courtyards in San Francisco, as well as different small walls that we've built.
These were installed in 2015 and so far have held up well. In the future, the company plans to put the entire assembly line, mixer, hopper, etc. into shipping containers so that biocement can be made anywhere. And by doing so, they may cement a brighter future for our planet. I'm Sikon Akpan, and this is Science Scope from the PBS NewsHour.